What's up, everybody? Welcome to the 19th lecture of Trig. Today we're going to be talking about section 3.4. To start off with, I thought we'd go over an example problem. I was thinking about the last example in the notes with the airplanes, but I think I'm going to leave that up to y'all. Instead, why don't we go over this example? So what we want to do is, given these two vectors u and v, we want to find the difference of 2u and 3v. So how are we going to go about that? What are we going to do? Well, the first thing we're going to do is we're going to put them in the same form. One's in that ijk form, and the other one is in our traditional component form. So the first thing, like I said, is we want to put them in the same form so we can actually do things with them. Okay. Let's start with u. U is going to be in the form 4, -3, right? All right. Well, we already know that v is in that same form, -3, 1. So now all we have to do is the arithmetic of all of this. So let's do that. This tells us that 2u is going to be equal to 8 -6, and v equal to -3, 1. Well, that tells us that 3v is going to be equal to -9, 3. So, putting all of this together now, we've got 2u, which we just calculated, minus 3v, which we also just calculated, sorry, typo. So, putting all of this together, we've got 8, -6, minus 3v, we said is -9, 3. Well, we're subtracting this vector from this vector. So what we'll end up with is going to be 8 minus -9. It's going to be the same thing as plus -9. Okay. My mistake. Minus -9 is going to be the same thing as plus 9. That's what I meant to say. And -6 minus 3, that's going to come out to be -6 minus 3. Nothing fancy there. Now we're just going to do the arithmetic. And what we're going to find is that this comes out to be 17, -9. And that's it. That's all there is to it. Cool. So let's start looking at 3.4 then. So up to this point, we've only really talked about scalar multiplication and vector addition and subtraction. So you might be asking, is there anything like multiplication with vectors? There is. There's two different things. One's called the cross product and one is called the dot product. Fortunately, in this class, I don't remember us having to go through the cross product, which is probably a good thing. It's cumbersome, or it can be cumbersome. But we do go over the dot product. And the dot product, pretty straightforward idea, actually. So we've got these two vectors. We want to take the dot product of the two of them. We say u dot v is equal to, and then we take the components in the x direction, multiply them together. Then we take the components in the y direction, multiply them together, and then just add those two products together. So we literally just go down the line. We say u1, v1 multiply together, plus u2, v2 multiply together. That's it. That's all there is to it. So as an example of this, we've got these two examples up here. Let's look at this first one. Well, we want to take u dot v. Well, this is going to be 3 times negative 1/3 plus negative 1 times negative 1. Well, we know that's just going to be 1. And 3 times negative 1/3, well, that's just 1 as well. It's negative 1, I mean to say. So what we'll have is negative 1 plus 1, or 0. And all I did here was say 3 times negative 1/3, negative 1 times 1, or negative 1 times negative 1, I mean, and then add those products together. As another example, we've got these two vectors s and t. We want to multiply them together, or we want to take the dot product of the two of them, I mean to say. So, s dot t is equal to component in the x direction times the component in the x direction. That's 5 times negative 4. Component in the y direction is negative 2 times the other component in the y direction. That's 1. So just go ahead and not worry about it, because anything times 1 is itself. So what we're left with is 5 times negative 4 plus negative 2. So this is going to come out to be negative 20 plus negative 2, which is equal to negative 22. Now, having said that, dot products do have a couple of particular properties that we want to worry about. The first property is that u dot v will always be equal to v dot u. Doesn't matter the order that we take the dot product. Anytime we have a 0 vector, and we take the dot product of it with v, well, that's going to come out to be 0, which makes sense, right? Because what we've got is 0 times v1 plus 0 times v2, that's going to be 0. U dot, the sum of two vectors, is going to be u dot the first vector plus u dot the second vector. This is a particularly important one here. Any vector dotted with itself is equal to the square of its magnitude, or norm. So let's see that really quick. Let's use our original vector u here. We want to take u dot u. Okay, u dot u is going to be equal to 3 times 3 plus negative 1 times negative 1. This is going to be equal to 9 plus 10, or 9 plus 1, which is equal to 10. Now, let's find out what the magnitude of u is. the magnitude of u is going to be equal to the square root of 3 squared plus negative 1 squared well, 3 squared is 9. Negative 1 squared is 1. So we have 9 plus 1 underneath the radical, or just the square root of 10. Well, if we square both sides, sorry, I have a typo in here. I forgot to put the double bars around either side of our u. But if we square both sides, we'll get the magnitude of u squared is equal to 10. So, per this rule, u dot v is equal to the magnitude of v squared. Well, it's just showed to be true, right? We just took the dot product of u with itself, found out that it was 10. Then we took and found the magnitude of u, found out it's the square root of 10. If you take the square root of 10, it's just going to come out to be 10. So it is, in fact, true. And finally, this last example, let's say we've got two vectors, u and v. We take the inner product of the two of them, or the dot product, and multiply it by a scalar. Well, that's going to be the same thing as if we multiplied either one of those vectors by the scalar and then took the dot product. And you'll see what I mean in just a couple seconds here. But having said that, let's look at a couple more examples. I know, I bet y'all are pretty jealous of this awesome Godzilla mug that my little sister got me. But that's not what's important right now, right? That's not what you came to this lecture for. You came to this lecture for these awesome examples. Now, before we get into these examples, there is something I want to point out to y'all. When talking about vectors, we might be tempted to say u times v. We can't. That has no meaning. Multiplying two vectors gives us nothing. It has no physical meaning for us. What does, however, is the dot product. So, u times v, nothing. Does nothing for us. You can't even, mathematically, can't do that. But, u dot v, we can do. And not just can we do it, this gives us a particular type of number. It gives us a scalar, right? So because this gives us a scalar, we can do this problem up here. And this is why I wanted to point this out, because otherwise we might be tempted to say, well, u dot v is a vector and a vector times a vector. No. U dot v is a scalar. A scalar times a vector is possible, but a vector times a vector is not possible. So having made that distinction, let's look at this problem. What we've got is u dot v, that quantity times w. So why don't we go ahead and just calculate what u dot v is first? Seems like the obvious logical thing to do. Okay. U dot v is equal to the dot product of the vectors -1, 3, dotted with 2, -4. So this is going to be 2 times -1. Plus 3 times -4, which is going to come out to be negative 2 plus negative 12. Negative 2 plus negative 12. That's going to come out to be negative 14. So, u dot v times w, because we can do that, right? This is a scalar. U dot v times w is going to come out to be the vector u dot v, that quantity times w, is going to be negative 14 times the vector w is equal to negative 14 times 1 negative 2, which is going to come out to be negative 14, 28. Dope. That was pretty quick, actually. Let's do this next one now. So for this next one, we first want to find out what 2v is, just because it'll be easier for us. 2v, actually, you know what? I'm going to change my mind on that. We're going to go at this in two different directions. We're going to calculate u dot 2v first, and then we're going to calculate using one of those properties and pulling out the 2. Okay. U dot 2v is equal to u dot 2 times the vector v is 2, negative 4. This is going to be equal to u dot 4 comma negative 8. So we have negative 1 comma 3 dot 4 comma negative 8, which is going to come out to be negative 1 times 4 plus 3 times negative 8, which is going to be equal to negative 4 plus negative 24 is equal to negative 28. Now, using that other property I was talking about, there was a property that said u dot 2v was going to be equal to 2 times u dot v. Well, we found u dot v a minute ago, negative 14. And 2 times negative 14 is in fact negative 28. So what's happening here? Why does that rule happen? Why can we do that? Well, if we trace our steps, look at what we've done here. We multiplied this 2 into 2 and negative 4. Well, that shows up here and here, right? So we can pull out the 2 here, and we can have just u dot v times 2. And that's why it happens. Cool. So let's keep moving on. All right. So for this next problem, I want you to find theta. How are you going to find theta? There's got to be a way if I'm going to ask you to do that, right? But It's not obvious right now, is it? Sure, we might be able to use the unit vector and find out what the angle from V to the positive x-axis is, and from what U to the positive x-axis is, and take the difference. We might be able to do that. Sure. But that takes a while. And it's 1:44 in the morning and I don't want to be here all night. So, what's the shortcut, right? The shortcut to this, the way we want to solve this particular problem, is we want to set up this particular relation. The cosine of the angle between two vectors is going to be equal to the dot product of those two vectors divided by the magnitude of both of those vectors. Okay, so in this case, the dot product of the two vectors, we can figure out all of this pretty quick and easily, right? U dot V is equal to 4,3 dotted with 3, 5, which is going to be equal to 4 times 3 plus 3 times 5 which is going to come out to be 12 plus 15 which is equal to 27. Okay, so we found the first part. Now, we need to find the norm or magnitude of U and V. Well, the norm of U is equal to the square root of 4 squared plus 3 squared, which is equal to the square root of 16 plus 9, which is equal to the square root of 25, or just 5. Now, the norm of V is going to be equal to the square root of 3 squared plus 5 squared It's going to be 9 plus 25. Which is equal to the square root of 34. So putting all of this together, we know then that the cosine of theta here is going to be equal to 27 divided by the quantity 5 times the square root of 34. So the angle is just going to be the arc cosine of 27 divided by 5 times the square root of 34. Dope. That was a lot quicker than going the other route. Now, there's an observation that we can make here as well. I'm going to erase all of this really quick. Well, not all of it, but erase some of this. Because what I want to show now is an observation that we can make from here. Notice if we multiply both sides by the norm of u and the norm of v, so the magnitude of u and the magnitude of v, what we have is the magnitude of u times the magnitude of v times the cosine of the angle between our vectors is equal to u dot v. All I did here was multiply both sides by our denominator. So what we've got here then is another way to calculate the norm, the dot product of two vectors. So let's say I just told you that u and v had a particular magnitude and that a particular angle was between them. You can still find out what their inner product is, what their dot product is. Inner product is another word that mathematicians use for the dot product. Actually, what we think of as the dot product is a very particular type of inner product. But that's neither here nor there. So, what I am saying is that let's say I told you that u has a magnitude of, let's say 4. That v has a magnitude of, let's just say 5. And that the angle between them was, let's say 30. No, let's say 45. It's a good number. 45 degrees. You can still find the inner product with that. You can still find the dot product using this information right here. What you would do is you would say, all right, dope. So I've got u dot v. This is going to be equal to 4 times 5 times the cosine of 45 degrees, which is the square root of 2 over 2. And we can do all of that math, and it's going to come out to be something that we can work with, right? That's all there is to it, really. Having said that, let's look at another example or two. So never mind that stick figure is about as 10 as I am. Earlier in the lecture, I had said that the inner product of these two vectors was equal to 0. Now I claim that there's a very special property about that exists between these two vectors, that there's a particular relationship of importance between them. I took the liberty to go ahead and draw it over here, and I'm wondering if any of y'all can see it. This vector, or these two vectors rather, they form a right angle to one another. The angle between them is 90 degrees. And we can see that just by taking the dot product and seeing if the dot product is 0. Now, why is that? What causes this relationship to occur? Well, the reason for that happens to be because of what we just did a second ago. We said u dot v is equal to the magnitude of u times the magnitude of v times the cosine of the angle between the two vectors. Well, what happens when theta is 90 degrees? Well, cosine becomes 0, right? So whenever the angle between two vectors is 90 degrees, their dot product will be 0. Or vice versa. Whenever the dot product of two vectors is 0, the angle between them will be 90 degrees. Now this is useful. This is really useful, actually. And it's useful because it lets us do things like answer questions that maybe I give you a vector and I ask you, find a vector that's perpendicular to it. Well, that means I want you to find a vector that's at a 90-degree angle to it, right? So how are you going to do that? Well, the first thing you can do is write out what the dot product would come out to be, set it equal to 0, and then solve for your values, solve for your terms. Now, I just said a second ago that two vectors with a dot product equal to 0 form a right angle to each other. Well, because this is a very special property, when this occurs, we give another designation to these types of vectors, these pair of vectors. What I mean to say is, if the dot product between u and v is equal to 0, if that's the case, then we say u and v are orthogonal to each other. So another way to think of this is on an exam, I might say two vectors are orthogonal to each other. Find their inner product. And that might be all I tell you. Well, their inner product is going to be 0 because they're orthogonal to each other. And that's really why we say that. It's a pain in the ass, frankly, sometimes to say u dot v is equal to 0. U and v are orthogonal. It's a little bit easier. It says a lot, actually, a lot. But anyhow, enough with this definition. Let's use it. We want to show that these two vectors are orthogonal. So what are we going to do? Well, we're going to take their dot product and see if it's 0. So let's do that. U dot v is equal to 2 comma negative 3 dot 6 comma 4. Well, this is equal to 2 times 6 plus negative 3 times 4, which is going to come out to be 12 minus 12 is equal to 0. And that's it. That's it. That's all I got. No, literally, that's like the entire lecture here. That is all I've got for y'all today. If y'all have any questions about all of this, please shoot me an email. I'll be happy to help. Having said that, have a good weekend, everyone.